Today we are going to discuss how to collect and view OpenShift cluster logs using Grafana Loki. Hey, what's up everybody? Welcome back to my channel. My name is Aleš Nosek and I'm the software practitioner located in San Diego, California, helping you navigate the world of Kubernetes. In the previous video, we used the Observatorium project to implement multi-regional monitoring system. In today's video, we are going to utilize Observatorium again, but this time we are going to focus on log collection for OpenShift clusters. For log collection, Observatorium makes use of Grafana Loki. You can find the official Observatorium project website at observatorium.io. And also the Observatorium project is hosted on GitHub. And here in the operator repository, you can find the instructions on how to deploy the Observatorium operator on your Kubernetes or OpenShift cluster. Before we get to the deployment part of the video, let's discuss the Observatorium deployment diagram first. At the front of the Observatorium deployment, there is a component called Observatorium API. Observatorium API is a facade which exposes Loki APIs to the outside of the cluster. And Observatorium API ensures that all the requests coming through these APIs are authenticated and authorized. The APIs exposed via Observatorium API component are the Loki push API and the Loki query and the Loki tail APIs. The Loki push API is used by the log collector, like for example Prometheus, to ingest logs into Observatorium. In our case, we are using Prometheus, which is a log collector that comes as a part of the Loki project. Prometheus allows you to, on the Kubernetes cluster, discover pods and collect their logs easily, but it can also collect logs from systemd, syslog, static files, and other locations. The Loki push API is also supported by other well-known log collectors, like for example Fluentd. So instead of Prometheus, you can for example use Fluentd. The other two Loki APIs exposed by Observatorium are the Loki query API and the Loki tail API. The Loki query API is an HTTP-based API which allows the client to pull a time range of collected logs from Observatorium. Client can also specify a filter for logs based on the LogQL, log query language, which comes with Loki. On the other hand, the tail API here is WebSocket based API, and that one allows the client to observe the logs as they are collected in the real time. In the diagram, I also depicted the two clients that I will be using later in the video. The first client is Grafana, and the second client is LogCLI. Grafana allows you to create dashboards to display the collected logs, but also Grafana supports a log live streaming functionality. Log live streaming leverages the WebSocket tail API so that you can follow the logs in Grafana as they are collected in real time. The LogCLI client, that's the client which I'm really excited about, comes as the part of the Loki project. And LogCLI is a command line client. So with LogCLI, you can watch your logs in real time and also query your collected logs directly on the command line. So far, we have discussed the front part of our deployment. Let's now focus on the backend. And the backend, that's the place where all the log processing actually happens. And for that, Observatorium will deploy the components of the Loki project. Let me now walk you through the log ingestion process. Prometheus is collecting logs, and by default, every 1 second, Prometheus will send the batch of logs in a request to the Observatorium API. Observatorium API will route the request to the Loki distributor component. Loki distributor will validate the request and it will split the incoming logs in the request into batches, and it will send them into multiple Loki ingesters so that those logs can be ingested in parallel. After Loki ingester receives a batch of logs to ingest from Loki distributor, it will keep those logs in memory, but also it will immediately write those logs into a write-ahead log. Write-ahead log is located on the local file system, and that file system is backed by a persistent volume. Only after logs are persisted, log key ingester will acknowledge the ingestion of logs, and only after that Loki distributor is going to respond to the client that logs were successfully ingested. While keeping the logs also in memory, Loki ingester in memory forms chunks of logs. Each chunk contains up to 1.5 megabytes of compressed logs, and after the chunk is formed, then Loki ingester will upload this chunk as an immutable block into S3 storage. Also, Loki ingester maintains an index of chunks, and that one is also uploaded into the S3 storage. Another component called Loki compactor then periodically compacts the index stored in S3 so that we can achieve a better performance. Let me now walk you through the process of how logs are retrieved. For that, a client like Grafana or LogCLI will send a log query request to the Observatorium API endpoint. Observatorium API will route the request to the Loki query frontend component. Loki query frontend is a stateless component similar to Loki distributor, and Loki query frontend speeds up the query path. It will split up the query into multiple smaller queries, and then it will distribute them to multiple Loki querier components so that they can be processed in parallel. Loki querier component is the component which actually processes the query. It will fetch logs from two different locations. Recent logs will be still available in memory of Loki ingester, so that is where Loki querier will fetch them from. Older logs have been already flushed and stored in S3, so Loki querier will fetch the older logs from S3. After Loki querier fetches all the logs needed to answer the query, it will send the result back to the Loki query frontend. And Loki query frontend, after receiving all the results from the Loki queriers, will stitch those results back together, and all the logs are sent then in the response back to the client. If instead of querying logs, the client is interested in tailing the logs in real time, then the client will open a WebSocket connection, which is proxied through the Observatorium API, and that WebSocket connection ends at the WebSocket endpoint of the Loki querier component. Loki querier will be fetching the fresh logs from the memory of Loki ingester over the gRPC, and will keep sending those logs back over the WebSocket connection to the client. Note that the Loki query frontend component supports proxying the WebSocket tailing connection as well. So the connection could go through Observatorium API through the Loki query frontend before the WebSocket would hit the Loki querier. However, in the Observatorium deployment, I have seen that actually the connection is configured to go straight from the Observatorium API to the Loki querier. I'm not showing it in this diagram, but each of the components is deployed as multiple replicas, with the exception of Loki compactor. Loki compactor must be deployed as a single instance. From experience, I learned that Loki ingester as well as Loki querier component require a lot of memory, as they are keeping the logs in memory. Observatorium will deploy these components with a memory limit of 200 megabytes, which is easily exceeded. So In the case that Loki query or Loki ingester exceed their memory limit, then the pod will get restarted. So if you are seeing your pods restarting, then make sure you add more replicas so that the load spreads across all the replicas and each individual replica will not run out of memory. Now that we have a good understanding of how Observatorium and Loki deployment looks like, we can discuss the bigger picture of how Observatorium can be used to collect logs from OpenShift clusters. In this diagram, I'm depicting one of the geographical regions we have. You can see that per region, we are deploying one highly available instance of Observatorium. In the region, there are multiple OpenShift clusters. We deploy Prometheus on each of those OpenShift clusters so that it can collect the logs from the cluster and send them to the regional Observatorium instance. The logs will end up persisted on the S3 bucket within the same region. We also use Grafana and LogCLI to query and tail the logs. If you are running your infrastructure in multiple regions, then you can deploy a Grafana instance and you can configure that Grafana instance with a separate Loki data source, one Loki data source for each of your regional observatoriums. And that will allow you to review the logs from any of your regions in the single Grafana instance. Also, you can use LogCLI and point it to any of your Observatorium endpoints, and you can review the logs from any of your regions using the LogCLI. Finally, in this part of the video, we are going to deploy Observatorium. As I mentioned before, Observatorium installation is documented in the Observatorium Operator Git repository. And based on the instructions included here, I created a separate Git repository called Multi-Regional Observability. This Git repo is actually a fork of the Git repo which I was using in the previous video. In the previous video, we were only deploying the monitoring components of Observatorium. So I extended this repo to also deploy Loki components of Observatorium. I will include a link to this Git repository as well as a link to the previous video down below. Before you deploy Observatorium, you should decide how you want to authenticate your clients. By clients, I mean Prometheus, which is collecting logs and pushing them to Observatorium, but also Grafana and LogCLI. Observatorium comes with two options for authentication. Option number one is to use mutual TLS. That means that you will need to generate client certificates for your clients. And the option number two is to use OpenID Connect. I included the links to the respective documentation in this README file. And I also discussed the mutual TLS authentication option in the previous video in great detail. I already deployed Observatorium into two other regions, and now we are going to deploy Observatorium into the last region together. For that, I cloned the multi-regional observability Git repository, and I will follow the instructions in the README file here. All right, so as a first step, we are going to create the Observatorium namespace. I'll open a new console, create the namespace. I'm logged into the OpenShift cluster running in the US East 2 region. Next, after the namespace is created, I will deploy MinIO, which is my S3 storage provider. And next, I will deploy the Observatorium Operator. All right, so both MinIO and Observatorium Operator are coming up. As a next thing, you will need to configure your certificates, your API certificate and client certificates. I already have it done. And so I can now deploy Observatorium instance. All right, so let's take a look. All right, so as you can see, the components of Loki are already coming up. At this time, Observatorium doesn't support deploying just the logs components, just Loki components. Instead, you have to always deploy the monitoring components as well, which we were showing in the previous video. So I have to deploy all of them. I paused the video for a moment so that the Observatorium components will finish deployment. So if I take a look at the number of pods now, you can see that we have several Loki components, and you can say that I created multiple replicas of ingester as well as querier. They are deploying one after the other, so there will be 10 query components if I remember. So they are still deploying. I can show you the configuration in the meantime. Will be in Observatorium instance, and then I created an overlay to add Loki deployment. That's the Observatorium, and this is the Loki part of the configuration for Observatorium. You can see here that I chose the replicas this way. I have one compactor, as I said, that must be that way, 2 distributors, and then a lot of ingester and queries, as I realized they are easily running out of memory, and then 2 query front ends. Also, I wanted to change the size of the volumes which are used to persist logs on the local file system, but realized that actually when you add this configuration here, this configuration seems to be ignored, so I filed the respective issue. As a next step, we are now going to deploy Prometheus, that is the log collector. So I will go back to the README file, and here at the bottom I have the instructions. So remember that again you will need to modify those customization files to include client certificates in case you are using mutual TLS. So I already did that, and so I can deploy Prometheus, copy paste it here. Prometheus is deployed as a daemon set so that there is one Prometheus instance running on each of the OpenShift nodes. And as a last component, we are going to also deploy Grafana. So again, going back to the README file, scroll down a little bit. I'm using Grafana Operator to deploy Grafana. So first I'm going to deploy the operator. And right after that, I will deploy the instance. Again, remember to add the TLS client certificates for Grafana before you deploy it. So, and now we can take a look. As you can see, I also modified the customization. I added additional 2 dashboards for the other 2 regions. So I have in total actually data sources for the other 2 regions. So in total, I have 3 data sources configured in Grafana. So I will take a look at all the pods running here now. You can see that this namespace is pretty busy. Everything is sitting in the Observatorium namespace. Next, I wanted to show you how I configured Prometheus to collect OpenShift logs. And for that, I took a look at the existing OpenShift logging components and how they do scrape logs. You can find them in the OpenShift logging namespace. I have them deployed here as well. So OpenShift logging is using FluentD as a log collector, and then it is storing logs in Elasticsearch. So let's take a look at the configuration of FluentD. I can do OC page. That configuration is stored on, let's see, fluent.conf. Is here. Save it as fluent.conf. I'm copying it out of the container to the local file system so that we can use VI with the syntax highlighting so that it has more colors. Alright, so this is the FluentD configuration used by OpenShift to collect logs, and the interesting part in this configuration starts really more towards here. Pretty much need to look for source. I will start from the top. So FluentD configures Prometheus metrics, exposes metrics, but here you can see the first source really used. So as you can see, FluentD is collecting the systemd journald logs. That's one thing. Next, FluentD is also collecting all the container logs of all the containers running on a given node. And then I have seen here that we are also tailing the audit D logs from var log audit log. And as a next source, I'm seeing that FluentD is also collecting the Kube API server audit logs from this location here. And last two pieces, we are also collecting OpenShift audit logs. So the FluentD will find them in the var log OAuth API server audit log, and then we are also collecting the OpenShift API server audit log. So if you look at the rest of the file, there is no other sources that FluentD is pulling from. So based on this, I created a equivalent configuration in Prometheus, and that Prometheus configuration can be found in Prometheus overlays, Observatorium, conf, and it's the Prometheus YAML file. So the Prometheus is really deployed as a daemon set. So there is one instance of Prometheus running on each of the nodes, similar to FluentD running on each of the OpenShift nodes. So you can see that at the top of the configuration, we are saying where Prometheus should push the logs to. So this is the Observatorium, which happens to be running on the same cluster, so I can use the service. That Observatorium API is using a certificate which I created myself, so I need to be able to have the client validate the certificate, so I'm using the CA file here. And then also the Prometheus client needs its own certificate file and its own respective private key so that it can authenticate against the Observatorium API. Then you can see that I created or configured here several external labels. So these are labels which are added by the Prometheus to all the logs collected. And I am setting the hostname label because I'm collecting logs from different host names, different hosts. So I want to make sure that I can distinguish them. And then also, because I'm having multiple clusters in the same region, I'm also naming my clusters with a unique identifier. This particular cluster is called my cluster. And then next are the scrape configs. So first I configured the scraping of systemd journald. So this is how the configuration looks like here. I took it from the example files from the Loki project. Then I also configured the scraping of the audit logs. So these are exactly the locations which I have seen in the FluentD configuration. So audit logs for 3 API servers, Kube, OpenShift, and OAuth API server, as well as the audit logs from auditd. And the last part of the configuration is the most complex. No, I didn't create this myself. Instead, I copied this configuration over from this script, which I'm linking here. And by the way, even that configuration in that script was not really created by a human, but actually is generated by another script. Overall, this configuration will scrape all the logs from all the pods and containers in them, and will apply the proper labels to them. So there will be labels with the pod name, label with the container name, label for the namespace where the pod is running, and so on. I will show it to you in a moment. Let's view the logs using Grafana first. This Grafana instance has been configured with 3 different data sources so that we are able to view the logs collected in 3 different regions. And I didn't really create any dashboard for viewing logs, but instead I'm going to use the Explore functionality in Grafana. So now I am ready to start typing my LogQL expression to select the logs I would like to view. You can see that Grafana is showing me all the labels available which I can choose from. The unit label is used for logs which were generated by systemd journald, and it's the name of the systemd unit which generated the logs. Then for pods or containers, there are the namespace label, then the instance, which is a name of the pod, and then also there is the container name of the container within the pod. And then I also have audit label for all the audit logs, so API server audit logs as well as audit D logs. And then there are those external labels which I configured in Prometheus with the name of the cluster and also with the name of the host from where the logs were collected. As an example, let's view all the logs which were generated in the Observatorium namespace. So for that, I'm going to use the label namespace, which must be equal to Observatorium. I can execute the query by Control-Enter. And here we go. These are all the recent logs generated by any of the pods in the Observatorium namespace. I can also watch the logs live as they are being collected. So Grafana is now hailing the logs, and new logs are showing up at the bottom of the screen. I can also run the very same query towards the other regions. So if I would like to see all the logs from the Observatorium namespace which were collected in the Frankfurt region, I have them right here. And same, I can see the recent logs in the Observatorium namespace in the Singapore region as well. If I would be interested only in logs which were generated by a single pod, then I can continue my query, and I will pick the label instance because that's actually equal to the pod name. And then Grafana is going to offer me all possible names of all possible pods. That's because Grafana cannot know that there is a hierarchical relationship between namespaces, pods, and containers. However, I know that the pod which is running in Observatorium namespace is the Prometheus pod, for example, this one. I can complete my query and run it. And here we go. These are the recent logs generated by this particular Prometheus pod running in the Observatorium namespace. You can see all the labels which are associated with this one log line. So this one tells me even the location from where exactly this log line was scraped from, the host name, so the name of the node, and also the name of the pod. And also Loki parsed some of the information from the log line for me. The very exciting part of the Loki project for me is the command line interface, and that command line LogCLI allows you to query your logs and also tell them in real time just using the command line. So I find it really great. So in order to connect the LogCLI to our Observatorium, we first need to find out what is the Observatorium endpoint. So let me get all the routes in the Observatorium namespace. And you can see that this will be our host name here. So I can now type LogCLI. Address of the server is, I'm connecting over HTTPS, and then the host name, and then at the end there is a path which I cannot remember now, so I will grab for it something called logs. Here are some examples. So it's API logs v1 default. This part of the path at the beginning, those are actually this is the Observatorium APIs where I'm connecting to the tenant default, and what would come behind would be then the Loki API. I'll paste it here. This one out. And then I also need to tell the client to use the client certificate when talking to the server. So that I will use the Grafana cert I have here and the private key. And I also will tell the client that the server cert was signed by a specific CA whose certificate is right here, so we can validate the server cert. And the command I'm going to run is called labels, which will allow me to discover all the possible labels which are available in this Loki instance. And also I can take a look at all the values which those labels have. So let's say that I would like to find all the possible namespaces from where we collected logs from. And here they are. So that I don't have to type the long command again, let me create an alias here. So that was this command here. Let's see, lc. So that's one, and I'll just use this part of it so that I can now do lc labels to achieve the same as before. As an example, let's again retrieve all the logs which were collected in the Observatorium namespace. So for that, I will use my LogCLI client, and I would like to run a query where namespace is equal Observatorium. So you can see that each of the lines is annotated with the labels which are attached to it, and this is the here actual log line. And also you can notice that Loki client will by default, if I count the number of lines, will actually only retrieve 30 lines by default, which is pretty low limit. So I can actually increase that limit. I can say that hey, give me like 500 lines, right? And will be many of them. If I just count them again, then there will be 500, because there is at least 500 log lines for sure collected in Observatorium namespace. So, and also if I want, I can show a tail. So let me tail the logs. And you can see that the logs are being collected, and I'm seeing them in real time. Here and there a new log comes in at the bottom. Yeah, right now. To get an idea of what is the latency of LogCLI tail command, let's run a small test. In a namespace which I called Loki test, I have a pod which generates a message every second. And so we can use oclogs-f to tail those logs from that pod. So here we go. Every second there is a new line. So now we would like to do the same, tail the logs, but using the LogCLI. So for that, I am going to put together the LogCLI command. lc will be a query. I want to tail that particular log, so instance equals, and the pod name, this one. So, and I will tail it, and also I will just display the logs so that we can see them side by side. Be fine. Okay, so at the bottom you can now see the new lines coming in, and there may be around 1 second latency, something like that. I think it is pretty impressive. Let's review what we covered in this video. We discussed the Observatorium architecture diagram, and we have seen that at the front of the Observatorium deployment, there is a component called Observatorium API. Observatorium API is a facade which takes care of the request authentication and authorization. We have seen that Observatorium deploys several components from the Loki project. Loki components are actually the ones which process the logs, and the logs are for the long-term storage stored in an S3 bucket. We have used Prometheus to collect the logs from OpenShift clusters and push them to Observatorium, and we use Grafana and LogCLI to view the logs stored in Observatorium and also to tail the logs in real time. We discussed how you can collect logs from multiple OpenShift clusters within the same region. And we also view logs from multiple regions using one Grafana instance. I hope you enjoyed today's video. Please feel free to leave your questions or comments down below. If you found this video helpful, please consider subscribing so that you are notified whenever I release a new video. Until next time.